Hi, in this video I would like to introduce the ideal gas equation and also different forms of the gas equation that we can use with algebraic manipulation to get variables other than those that are in the equation. So we see right here we can have the ideal gas law PV equals nRT, and say for example we can divide by the volume, so the number of moles divided by the volume, and so rearrange for the concentration. So we can do that and end up with, so we can rearrange for molar concentration, number of moles per volume, and we can then find that this is the number of moles over volume equals the pressure over RT. So we can find the concentration of a gas by taking the pressure and dividing by R times the temperature, and we then find the molar concentration, so we end up with units of moles per liter. Likewise, we can, knowing that we can find the mass of, if we know the number of moles, we can find the mass of a substance, again knowing that the mass of a substance is the molar mass times the number of moles that we have. So say you look up the molar mass, multiply it times the number of moles, and if we multiply each side of this equation right here by the molar mass, so if we do that, so if we multiply the molar mass times the number of moles divided by the volume and equal that to pressure over RT times the molar mass, and instead of canceling that out, we can see right here, if I get mass, I multiply the mass, the molar mass times the number of moles, I end up with a mass, and mass over volume gives us the density. So if we then have an easy way to find the density of a gas with the same kind of relationship right here. So we can then rearrange that over mass over volume equals the pressure of the gas times the molar mass divided by RT. So if you know the molar mass of a gas, you can then find its density. Let's do an example calculation. Say we want to find the density of carbon dioxide. All we have to so let's do that. Calculate the density. Of CO2 at 25 degrees, let's say a little warmer than room temperature, 25 degrees Celsius, and 1 atmosphere of pressure. So a little bit higher than standard temperature and pressure. So all we have to do right here, the density then is equal to the pressure times the molar mass divided by RT. And then we just plug this in. We have 1 atmosphere times the molar mass of carbon dioxide, which is 44 grams per mole, and divide that by R, which is the ideal gas constant, and the temperature, 0.08206 liters times atmospheres over mole times Kelvin is the unit, times the temperature, which in this case is 25 degrees, so it's 298 Kelvin. And we calculate this, and we obtain a density of 1.80 grams per liter. So if we compare this, say, to the density of air, it is lower. The density of air is about 20-something grams per mole if you average together the densities of oxygen and nitrogen, which are the major constituents of air, and multiply them by their appropriate molar fractions, which we'll do next week, we'll see that the density of air is smaller because this molar mass of air is effectively smaller. Oxygen and nitrogen have smaller molar masses, so therefore the density of CO2 is quite a bit higher, so CO2 tends to sink. So this is pretty useful to say, for example, in fighting fires. Carbon dioxide fire extinguishers smother a fire because it travels along the bottom. So you might have done this experiment where you can snuff out a candle carefully by bubbling, say, carbon dioxide from another container to another. Likewise, carbon dioxide can asphyxiate people sleeping near the ground. If there's a carbon dioxide source, like happened in some volcanic lakes that spew out carbon dioxide, the carbon dioxide can be emitted, say, for example, when people are sleeping, and asphyxiate people. So there's two sides to that coin. Here, another problem. See if you can do this. Thank you for watching.